Hello and welcome to this new video where we discuss mathematics and physics on the board. In this video, what we are going to do is again actually look at an application of the Legendre transformation in physics. In this particular case, what we are going to see is that it's not like it's a virtual thing to do to apply Legendre transformation. It has actually concrete application in the real world when we try to understand the forces, for example, between different things, or the driving mechanisms behind something. Okay, and in this particular case, it's a famous example of the plate capacitor in electricity, and how basically misunderstanding what we are doing can lead to paradoxical situations that are resolved by using a Legendre transformation. Okay, so here I'm just, as usual, setting the stage. There's plenty of setting stage aspect here, but let's start with the basics. And again, as usual, if there is anything that basically you're not understanding, or this is going too fast, or I'm not aware of this stuff, by all means, do let me know in the comment section, and I will be happy to expand upon these different points. So what we are considering is a simple parallel plate capacitor, okay? And basically what it's constituted of is you've got two plates, and these plates have been charged plus Q and minus Q. So they have equal magnitude but opposite sign on either plate. And then there is between these two plates voltage or an electrostatic potential difference that is delta V. Okay. Now, from the theory of conductors, then it turns out that Q, the charge that is accumulated on either plate, the magnitude of the charge can be written as C times delta V, and C is what people call the capacitance. Now, in the let's say basic theory, we assume the capacitance to be essentially a constant number that does not depend on time, does not depend on whatever the frequency, does not depend on anything. So that's a number. And it turns out that this number, you can get an estimate of it by doing very simple calculations. So again, if this is something you would like me to go through, by all means, I would be happy to. But essentially, you can show that if you look at a dielectric medium here, that is considered so-called dielectric, isotrope, homogeneous, and linear, then basically you're going to have this expression here. There is also basically that we don't care about the frequency, so we are looking at a static case as well. So the capacitance is epsilon, so epsilon here is a dielectric permittivity of this medium. S is a cross-section of the plates, and L here is the, I didn't mention actually, L here is the, there's a distance here between the two plates. Okay? So basically that's what we have. And then if you do a basic electricity theory, you're going to see that the stored electric energy in a capacitor can be written in two equivalent fashion, at least in circuit theory. And that's half of C delta V squared. And if you substitute delta V by Q over C, you're going to get an equivalent equation or for the energy, which is half of Q squared over C. So when you look at circuit theory, and then how this is going to impact whatever the current magnitude over time in an LC circuit, in an RLC circuit, and so on, that's all fine. Nothing is going to be troublesome. You can use either of these equations for your, depending on what you do, on what you want to do, and the strategy you adopt, etc. It's all fine. Now, the case I want to look at is a bit different. The function C here, the capacitance, is a function of L, the distance between the plates. And what I'm interested in here is plotting the electrostatic energy stored in the capacitor as a function of L when I actually, with two different experimental conditions. The first experimental condition is you fix Q, so you use the equation on the right-hand side, and then in that case, the energy is actually a straight line from zero, and then basically simply increasing as you increase the distance away from the plates. Okay? Then there is another case where experimentally what you impose is delta V. Okay, so you impose a voltage and you separate the plates. Now, as you put that into that equation, you're going to see that C here is 1 over L, so it's actually going to diverge at L equals 0, and basically is going to go to 0 that way. So what we see is that in one case, if you fix Q, so the charge on the plates, and you separate them, then you're going to have a linear increase in the energy, while if you actually fix delta V according to this equation, you're going to have a 1 over L decrease of this particular electrostatic energy. Okay? Now, the reason why this is interesting is because if we assume that this is really stored electrostatic energy, then it tends to, tend to reason to assume that we can obtain the electrostatic pressure from it. After all, we've got an electrostatic energy. If we differentiate that electrostatic energy with respect to L, the separation between the plates, then we should actually get the corresponding driving force between them, which we will interpret as being the electrostatic pressure. So the thing here is that usually you would define this like this, so it's minus, and then the derivative of the electric energy, and then divided by the the spacing L between the plates, and here you need to divide also by S as a cross section to actually get some pressure. Otherwise, you will just get the force. So what happens is that if you do it in the case of fixed Q, what you're going to get is basically this expression, minus Q squared over 2 epsilon S squared. That looks a bit horrible, but if you actually replace Q by being sigma over S, where sigma is a charge density on the plates, you're going to get that this is minus sigma squared over 2 epsilon. Now, this particular expression here turns out to be consistent with electrostatics. You obtain a negative pressure, but negative pressure means that essentially these things are attracted toward each other. Now, if you look, you actually have a positively charged plate and a negatively charged plate. So their electrostatic interaction should be attractive. Okay? So basically this result is consistent with electrostatics, and in fact this one is basically the field that is emitted by one plate times the charge of the other plate. That's essentially what it is. So basically that's it. So this one seems to be fine. But now if we instead try to look at this in the case of the fixed voltage difference between the plates, so we look at the pressure that we would get from this, then we get half epsilon delta V squared over L squared. This thing is actually positive, and this means that there is a repulsion between the plates. And the question is, well, that doesn't seem to be consistent with the physics we see here. So the question is, did we miss something here? And the answer is yes, and we are going to solve that by using a Legendre transformation. So here, what we are going to assume is that it's actually the real one that we want to look at that seems to be okay from a physics standpoint turns out to be this electrostatic energy. Okay, insofar as we are willing to, for example, vary L as well. Okay, so what that means is that we start as on the ground that E elec it's actually a function of Q and L, and that's equal to that. So half, and then I need to replace actually. So that's C is equal to, so let's say that's Q squared epsilon S L. All right, so that's what we have. Now, what I'm going to say is the following. What we want to do is basically, by the way, this function, although it doesn't look like it, it's actually convex. It's convex in Q, if you want to look at it. So this function is actually quadratic in Q, so it's convex with respect to Q. So then, if I apply the principle of Legendre transformation, what I want to do is I want to find a function that preserves the physics of that stuff, but then will be in function of delta V instead of Q there. So it's as if, again, I wanted to express a function, not in terms of the actual variable I was looking at before, but in terms of another one that is a sort of dual of it, like a slope or something. That's basically what I want to do. So what I want to do in principle is basically I want to find E elec star such that I've got and I don't know yet what it is. So what I'm going to say, I'm going to put a P here because that's what I used. So you can check in the, so that's at fixed L, all of that. But again, that's at fixed L, but starting from the presumption that this equation is fine even when L varies. Okay. So now I'm applying it on P, and what I want is that this is going to be E elec and then of QL. And then here, because I don't know what it is yet, I need to say that this is D elec dq, and then Q. And then basically, that's what I call the P for now. And then I replace by P, by Q of P. Okay, that's what in principle I need to do. Now, very rapidly, we are going to see that this is okay, because if you do d elec of dq, what you're going to find is that you're going to get P is equal to QL epsilon S. And if you check on the board we've seen earlier, this is actually delta V. Okay, so the bottom line is that what we are asking is P can be replaced by the electrostatic. Here is delta V. L. What we need to use is actually E elec of QL minus delta V Q. And then that's expressing Q as a function of delta V. And as we know, Q is equal to C delta V. So C delta V, but let's replace with the actual values just to be on the safe side. So here I had QL epsilon S, and so that means that Q is equal to epsilon S delta V over L. Okay, so that's what I need to do. So if I do it, then what I get is the expression where we have half. And in fact, here I can directly use C delta V square. I know this is what I'm going to obtain. And C, this is epsilon S. So epsilon S, and then over L delta V squared, and then minus, and what you're going to see here is that this is epsilon S delta V squared over L, and therefore the actual Legendre transformation of this function, which is the real one that captures the physics. If you actually, so again, this is describing the same function, simply with a different variable, which is the one you're going to control experimentally. It's actually minus half of C delta V squared. Okay, so that's the real one to be using. Now, what is interesting is that is in terms of interpretation. Okay, so what you notice here is that the electrostatic energy you're caring about here, like the real one, if you will, is going to be this minus that. Okay, um, and you can view that as the energy you need to actually that is stored as you move the plate at some distance. Fair enough, from some reference distance. And here, this corresponds to essentially it can be viewed as the work you need to do to that you had to do when you did that in order to carry all the charges at that particular delta V. Okay, so basically the delta VQ again is tied to L via this relationship. So it's not like there is no tie between L and all these guys. Is basically the amount of work, the supplemental amount of work you had to do in order to keep the charges constant as you made the plates further and further away. Okay, and you don't need to do this extra work if you simply impose a potential difference between the plates. And so that's why you actually get this particular expression. Now, keep in mind, this expression can be with a plus or whatever, that kind of doesn't matter. There can be a reference value that is like larger than 0 and so on, but that's kind of the idea. So if you were to plot that one, then it would actually be minus infinity, and then it would actually go to 0. But it starts from minus infinity and then it increases to 0, and therefore the corresponding electrostatic pressure you would get would be minus that. Okay, so that would still be actually okay now and consistent from a physics standpoint. Okay, so this is just to show you, like in a very concrete example, how the electrostatic energy, depending on how you look at it, can lead you astray depending on different experimental conditions you want to control and then work with. You can basically get to paradoxical results if you don't apply basically correctly how you go from one constraint where things are safe to another constraints with the same physics. Okay, so I hope this was a little bit illustrative of where the Legendre transformation can actually be useful, and in fact that it's not simply like a mathematical fantasy. This is actually useful to make predictions about experimental outcomes when it comes to different way of setting the experiments. So basically that's it. If you've got any questions or comments about this, by all means, do let me know in the comment section. Otherwise, see you in the next video.